I hope by now all of you are aware of the test dates for test 3 and the supplementary test. Remember, the supplementary test is only for two types of students. The first is those students who have missed any one of the tests for whatever reason that you missed it. And the second group of students who can write the supplementary test is those who do not have a course average of 50% or more. Now, if you are in that second category where you have a grade that is less than 50 and you write the supplementary test, that means the maximum grade you can get is 50%. You will not pass with anything other than 50%. So please try and avoid writing the supplementary test as much as possible. Do the tutorial tests. All of them will count towards your final grade. So please make sure that you do that. Okay, this week's tutorial test is online. I hope some of you have started already. Again, like I always say, you need to follow the instructions for answering the questions. If it tells you not to leave space, then leave a space. Do not leave a space. And if it says 2 decimal places, that is how you must write it, even if the answer is correct to only 1 decimal place, then add a 0 at the end, or however you need to rewrite it so that it is correct to the number of decimal places specified in the questions. Okay, so today we'll finish off on logarithmic inequalities. We said that there are 2 types that we look at the questions, or 2 ways that we solve them. So when we have a logarithmic inequality, when we have a logarithmic inequality, this is log of a base b. Now, depending on what your value of a is, we say this is less than c. Depending on what your value of a is, what you will do is you'll have a log of a base b, and then a to the power of c. Now, if a is greater than 1, then the inequality will remain and face in the direction it has been facing. But if your your a is between 0 and 1, then you'll rewrite this as log base a of b, and then you switch the side that the inequality is facing. So when you have a half here, for example, 1 over 10, whatever, any number that is less than 1 as your base, then you switch the side that the inequality is facing. But if your base is greater than 1, then you leave the inequality in the direction that it is facing. And then we always have to keep in mind that our logarithm, log base a of b, it must be defined. Now this logarithm is defined when our argument is greater than 0. So we need to ensure that on top of what we calculate over here, our argument must be greater than 0. So we're combining these two. So this one up here, this is what you work out, and then you make sure that it coincides with your argument being greater than or equal to 0. So if only this star over here is met, but the inequality over here is not, then your logarithm is undefined. Then you don't even have a solution. Okay? So you have to make sure that both of them are included. And remember what I said about both being included, that means when you stand on your number line and you look up, you should be able to see 2 lines if there's 2 conditions, 3 lines if there's 3, and so on. So let's look at one more example. We have log of 2, this is x plus 3 plus log base 2 x minus 3. This should be less than 4. So you have to keep in mind your laws of logarithms when you're solving this. Here my bases are the same. Both logarithms have a base of 2, so I can combine them, and because I am adding over here, I can multiply the arguments. So I have log base 2 x plus 3 x minus 3. This is less than 4. Then I will I will exponentiate both sides, so it will be 2 to the power of the left hand side and 2 to the power of the right hand side. And because 2, my base over here, is greater than 0, my inequality is not going to change the direction. So I have 2, I have log base 2 of x plus 3 x minus 3. This is less than 2 to the power of 4. And then from our laws of logarithms, we see that the base of the exponent is the same as the base of the logarithm. Then the answer is just equal to the argument that I have over here. So this is x plus 3 x minus 3. This is less than 2 to the power of 4, which is 16. Now this will lead us to a quadratic inequality, which we know how to solve. We said we will have to factorize, and I know you may be tempted to say, okay, it's factorized, I must find the critical points. No, not yet. That is because on the right hand side I do not have 0, I have 16. So I will have to bring the 16 over and then factorize again. So first I should multiply out the brackets. So I have x times x, this gives me x squared. X times minus 3, this is minus 3x. 3 times x, this is plus 3x. 3 times minus 3, this is 9. Then I will subtract 16, and this should all be less than 0. So these two will cancel, because negative 3x and positive 3x add up to 0. And then what I have left is x squared minus 25 is less than 0. Now this one, you will have to factorize it. You can use the difference of squares or factorize it the way we normally do, that you look for two numbers, that when you multiply them, the answer is 25. And when you add them, the answer is 0, because you can see in the middle over there, the coefficient of x is 0. Okay, so you look for two numbers, when you multiply them, the answer is 25. When you add them, the answer, negative 25. And when you add them, the answer is 0. So those two numbers are 5 and negative 5. So when I factorize this, what I will have is this. I have x minus 5, x plus 5. This is less than 0. Okay, so now that it's factorized and I have 0 on the other side, what I need to do is work out my critical points. So I take my critical points. The critical points are the values of x that make the factors equal to 0. So I have x minus 5 is equal to 0. This means that x is equal to 5. And I have x plus 5 is equal to 0. This means that x is equal to minus 5. Then what these critical points do is that they divide my number line. So I start with one number line, and then I put my 2 points, minus 5 and 5. on the number line, then you can see that my number line is now divided into three parts. I have the numbers that are less than minus 5 over here, numbers between minus 5 and 5, and numbers that are greater than 5. Okay, then I will extend, let me write this above, I have minus 5 and 5. Then I extend my number line to form a table. This is what we call the sign table. Then I have x minus 5, x plus 5. Okay, so I pick a representative in each of the regions, start with a number less than 5, less than minus 5, let's say minus 6. Then a number between minus 5 and 5, let's say 0. And then a number greater than 5, let's say 10. Okay, so the number you pick doesn't actually matter as long as it is in that region. It will behave in exactly the same way. Right, so we're interested in the sign of our factors, not in the actual values. So I substitute negative 6 minus 5. This is negative. Negative 6 plus 5. This is positive. And then 0 minus 5, negative 0 plus 5, positive. 10 minus 5, positive. 10 plus 5, positive. Then in the last row, I write my product. This is x minus 5, x plus 5. Okay, and you can see, yeah,
Miss
yeah,
is
Negative
negative
6
6
minus
plus
plus 5 is negative 1.
the first one.
And the first one
Plus
for
5.
x plus 5.
The first
It's
one, it should
negative.
be negative. Yes.
Mhm.
Okay, thank you. That is correct. Okay, then what you do is you can see my factors over here are multiplying, so I should also multiply my signs. So negative and negative, this will give me a positive, negative and positive, this gives me a negative, positive and positive, this will give me a positive. Okay, then I go back to my question after I had factorized, which is this one here. And I'm going to write it again at the bottom. So I have x minus 5, x plus 5, and I say this should be less than 0. Now I'm not taking the positive one or the negative one. What tells me what I need to take is this sign over here, less than 0. So it's not a rule that you must always choose the positive one or always choose the one in the middle. No, you look at what you have over here and decide what that means. Less than 0, this means negative. Okay, then you go to the last row and you look for the column that gives you a negative, and you can see I have negative over there. That's the one in the middle. So my solution over here will be from minus 5 to 5. That is the solution from the inequality. And then I need to include the conditions so that the logarithms are defined. So very important. So let's go back to the very beginning. This are my logarithms. I need to make sure that this is defined or it's valid. And the same thing over here, that this is defined and valid. And it must fit into the solution that I just got now. Because if one of them is not defined, the whole thing is not defined. Right. So this between minus 5 and 5, this just satisfies the inequality that I was looking for. And now for my logarithms to be defined, what I need is that their arguments are greater than 0. Now the first argument I have is x plus 3. So x plus 3 should be greater than 0. And The second argument is that x minus 3 should also be greater than 0. So the arguments of logarithms are always positive. So from the first one, this is the first argument, that is the second argument. So from the first argument, I get x is greater than 3, negative 3. And then from the second argument, I get x is greater than 3. So 1, 2, and this condition over here, all of them must be met. So you're looking for a place on the number line where all those conditions are met. This one over here means you want your number to be between -5 and 5. This one here, you want a number that is greater than -3. And this one means you want a number that is greater than 3. So you go and draw a number line. You put the very first one that we got, which is that it must be between -5 and 5. So our circles are unshaded because -5 and 5 are not included. Okay, and then the definition of the logarithms, we say that x should be greater than -3. Now -3 is somewhere here. So I put an open circle because it is strictly greater than -3, and greater than -3 means I am going to the right of -3. And then the second one, for the logarithm to be defined, we said greater than 3. 3 is somewhere here. Then my circle is open because 3 is not included, and then I go to the right of 3 because I want numbers that are greater than 3. Now what you're looking for, remember, is all the 3 conditions to be met. Now if I'm over here, none of the conditions are met because this number is not between -5 and 5. It is not greater than -3, and it is not greater than 3. So none of the conditions are met. Now if I am over here, only this one is met, and then the other 2, they are not met. And then if I am here, let's see, if I'm over here, only that one and that one are met. But remember, I want the region where all the conditions are met. That means when I look up, standing on my number line, I need to see 3 lines above me. And the only place I can stand is in this region over here. So if I'm standing between 3 and 5, I look up, I will see that this condition is met because I can see the line above me. This condition is met because the line is also above me. And this condition is also met because the line is above me. So my solution will come from this region. So I can rewrite this. So the solution in interval notation, this is 3 to 5. So 3 is not included because of the open circle over there. 5 is also not included because of the open circle over there. And then if I were to draw it on the number line, this is what I will have: 3 and 5, and my circles are open like that. Okay, so that is how you would solve any logarithmic inequality. Do we have any questions on logarithmic inequalities? Okay, it seems that you guys are fine. That's good. Then we move on to the second last chapter of the course, which is on sequences and series. Okay, now a sequence is just a list of numbers in a given order. So we start with sequences. So this is a list of numbers and they are in a specific order. So it's not random, there is a pattern to the way that the numbers are given. So we can look at an example. We have 2, 4, 6, 8, and so on. And then you can predict what the next number is. This one is simple. You can say the next number is 10, the number after that is 12, and so on. Okay, now our terms of the sequence, we denote them. So these are denoted by A1, A2, and so on. You get to the nth one, then next one is n plus 1, and then they continue in that manner. So A1 here, this will be our first term. A2, this will be our second term, and so on. So if I want the 50th term, I will just say A sub 50. If I want the 20th term, A sub 20. And then for a general term, we denote it with N. We say N. This is the nth term. And this is like a general representation. So this represents all the terms. So this is what a term will look like, the nth term, or sometimes called the general term. Okay, then this integer n that we have over here, this is called the index of an. So n is the index of an. Okay, so it is similar to the way that we write logarithms. They're not the same size. The n is a subscript. It is smaller than the a. Now we can look at some more examples of sequences. Let's say I give you a sequence 1, square root of 2, square root of 3, 2, and then I say it continues in this manner. Now here, what we try to do is come up with a formula for the nth term. Now if you look at this, you'll notice what is happening. So I started with 1, then take the square root of 2, the square root of 3, and then this is the square root of 4. So what happens is if I'm looking for a1, this is just the square root of 1, which is 1. a2, this is the square root of 2. a3, this is the square root of 3. a4, this is the square root of 4, which is 2. So if I want an, this is just the square root of n. So this formula over here is the formula for the nth term. So when I ask you what is the nth term in this sequence that we have over here, 1, square root of 2, square root of 3, 2, the nth term is just the square root of n. Because if I ask you what is the 1000th term, so a 1000, you know all you have to do is take the square root of 1000. If I ask you for the 15th term, all you do is take the square root of 15. So you can see my n over there, it goes under the square root. Okay, so this one is simple, not really much to do, just identifying the pattern, what is happening to the terms. Then you can have another one. We have -1, 3, -9, 27, -81, and then it continues. So the 3 dots represent or indicate that your sequence continues. It doesn't stop at 81. So it keeps going in that manner. So you try and see what is the pattern or what is happening here. Can somebody tell me what is happening here?
Um, 3 is being multiplied every time.
Okay. Okay.
So maybe it's okay.
Okay. So she says you multiply every term by 3. Okay, let's see if that is the case. So we start with -1. You multiply it by 3, you should get -3. But over here I'm getting +3. So I don't think that's right. So can somebody else tell me what is happening?
Yes.
Yes.
You multiply with a -3.
Okay, so I'm multiplying -3. Let's see. So I start with -1. I multiply with -3. Okay, I get +3. +3 times -3 is -9. Yes, times -3 is +27. And then 27 times -3 is -81. That is correct. So if I know the first term, to get the next one, I just multiply it by -3. Now this one, for the nth term, you can rewrite it like this. So we say an, this is equal to -1 to the power of n multiplied by 3 to the power of n minus 1. So we will work out how to get this formula or where I got it from, but for now it's just to see that yes, this actually is a formula for the nth term, because the way we described it, when I said every term to get the next one, you would have to multiply it by -3. Now that's easy if I'm looking for maybe 3 or 4 of the first terms, but what if I ask you for the 1000th term? That means you must know the 999th term, and in order to know that one, you must know the previous one and the previous one, and so on. Okay, so this formula over here tells us that if we want to know the nth term without knowing the previous one, we can use this. So let's see if this actually works. If I look for A1, this is equal to -1. See, my n is equal to 1, so I substitute 1. Then I multiply this as 3, 1 minus 1. This is just -1 to the power of 1, which is 1, because 3 to the power of 1 minus 1 is 3 to the power of 0, which is just 1. Okay, so for the first term, that is fine. Then for the second term, A2, so my n over here is 2. So this is -1 to the power of 2, multiplied by 3 to the power of 2 minus 1. And then this is -1 squared, which is just 1, 3 to the power of 1. And this is +3. And that is exactly what we have. So we can look at the third one, A3. This is -1 to the power of 3. That's my n. Multiply this by 3 to the power of 2. Sorry, not 2. 3 minus 1. Okay, so this is -1 cubed, that is -1, and then we multiply this by 3 to the power of 2, which is 9, and then I will get -9. So if we look at my sequence, that is also correct. Okay, so this is one formula that we can use to describe the nth term. Okay, so what you said, that you multiply each term by -3, that is correct. But with that one, you will need to know the previous term in order to get the next one. So if you don't know what the previous term is, it will be difficult to work out what the next one is. Okay, so we'll talk about
Miss,
how I got, yes,
for the formula,
yes.
-1 to the power n times 3.
Mm-hmm.
3 is from the sequence, or is it part of the formula?
It's part of the formula.
The 3?
Yes,
Or
this
it's
3 here is part of the formula. So for
and
now, I'm
-1?
just, -1 is also part of the formula. This is the formula that I gave you. I didn't tell you where I got it from. So we will talk about how to get this formula later on. But for now, we're just looking at terms in the sequence and can we find a pattern to describe them. So we will talk about how to get a formula like this.
Okay, Miss.
All right. So let's look at another sequence. We have 2, 4, 8, 16, and so on. Can somebody describe what is happening over here?
I think we just multiplied by
Yeah, multiply by?
2.
Okay,
2.
so exactly. So once you have the first term, you multiply to get the next one, you just multiply the previous one by 2. Okay, so now if I wanted a formula for a n, can somebody guess what the formula would be? So look at the previous ones that we did. The first one was square root of n. The second one was a little bit tricky, but we see that it works. Now what about this one? Can somebody guess how we could write this in terms of n? You're breaking up. 2n. Okay. So he says we should have 2n. Let's see if it works. We can say 2 times 1. Sorry, say again. You're breaking up. I can't hear you. Okay, so it's 2n. I can barely hear you. Okay, let's see that if 2n works. So the first one, 2 times 1. Yes, this is 2. That is correct. Then the second one, so I'm looking for a2. This is 2 times 2. So this is 4. And then the third one, a3. This is 2 times 3. This will give me 6, but in my sequence I have 8. So this formula 2n, that is not correct. So can we have another guess, please? Anybody to try? How can you write a formula for,
Miss,
yes,
Miss,
what
what
about
about
2 to
2
the
to the
power
power
n?
n?
2 to the power n exactly. So our formula an, this will be 2 to the power of n. Then we can always check and see if this is indeed correct. So we have a1, this is 2 to the power of 1, which is 2. Yes, that is our first term in the sequence. Then we have a2, this is 2 to the power of 2, which is 4. That's the second term in our sequence. Then we have a sub 3, this is 2 to the power of 3, which is 8. And then a 4, this is 2 to the power 4, this is 16. So you can see that this is indeed correct. So when you have this sequence here, we know that to get the next term, if you have the previous one, you just multiply it by 2, and we can write the general formula as 2 to the power of n. So here we're just using our intuition. Later on, we will actually rigidly work it out where you can see where we get the 2 to the power of n from. So from now, just want you to use your intuition and see how or guess what you think the nth term should be. Let's look at this one. We have 1, 3, 5, and 7. Can somebody tell me what the nth term is, or describe the sequence, how you get the next one? Either one. Either describe how you get the next term or give me a formula for an.
Miss,
Miss,
Yes.
I think it's 2n minus 1.
2n minus 1. Okay. She says 2n minus 1. Let us try. Can quickly substitute. We're looking for a1. This is 2 times 1 minus 1. This is equal to 1. So the first term is correct. Then a2, this is 2 times 2 minus 1. This is 4 minus 1, which is 3. And then we have a3. This is 2 times 3 minus 1, which is 5. And you can see that this is correct. So if I have the first term, to get the next one, I just add a 2. So you can see if I add 2, add 2, add 2. Or you can see that the general term is given by 2n minus 1. Okay, so that is fine. It's good. And let's look at half. 2 over 3, 3 over 2, 3 over 4, 4 over 5, and then it continues in this manner. So can you tell me either what the next term will be or what the general form will be, or describe it in words what is happening? So either of those. So I have half, 2/3, 3/4, 4/5. What comes next? Or tell me the an. Either one of those.
Miss Waro can take 6, so 5 over 6.
So the next term he says is 5 over 6. Yes, that is correct. And now can we describe what is happening here, or tell me the formula for the nth term?
Miss,
Yeah.
I think it's n over n plus 1.
Okay, very good. This is n over n plus 1. So let's look at our sequence. For the first term, in the numerator, I have n, and in the denominator, I have n plus 1. So this is 1 for term number 1, and then I have 2. The second one, I have 2, the second term, and in the denominator, I have 2 plus 1. 3, 3 plus 1, 4, 4 plus 1, 5, 5 plus 1. So this formula over here works. So I do not need to list 90 of them if I want to work out term number 99 or so on. So I know that A 100, this is just equal to 100 divided by 101. Okay, so that one is good. Then let us find the first 4 terms in a given sequence. So let's say I give you the formula for the nth term. This is minus 1 to the power of n times n. Now I want the first 4 terms as well as the 23rd term in this sequence. Now this is pretty simple to do because the first 4 terms means that n is equal to 1, n is equal to 2, n is equal to 3, and then n is equal to 4. So you just substitute n from 1 to 4 into that expression, and then that will give you the first 4 terms. Then to get this, the 23rd term, this just means that n is equal to 23. So let us work this out. Now a1, this is equal to negative 1 to the power of 1 multiplied by n, which is 1. So here the first one is negative 1. Then a2, this is negative 1 to the power of n, which is 2. And then you multiply by n itself, which is 2. This gives me negative, not negative, positive 2, because negative 1 squared is positive. Then a3, this is negative 1 to the power of 3 times the 3 itself. This is negative 3. And then a4, this is negative 1 to the power of 4 times the 4, which is positive 4. So the first 4 terms in this sequence will be negative 1, 2, negative 3, 4, like that. So the sequence does continue, but those are the first 4 terms. And then if I want to work out the 23rd term, this is just negative 1 to the power of 23 multiplied by n itself, which is 23. Now I know when I raise a negative number to an odd exponent, the answer is negative. So this will just be negative 23, like that. So when I give you the formula and I ask you to find the first n terms or whatever, it's just simple substitution. You just substitute a1, a2, a3, and so on. And if you're asked to work out a specific an, you just substitute that value of an of n into your expression. Let's look at another one. Let's say we have an, this is equal to n plus 1. So again, we want the first 4 terms. So a1, this is just 1 plus 1, which is 2. a2, this is 2 plus 1, which is 3. a3, this is 3 plus 1, which is 4. And then a4, this is 4 plus 1, which is 5. So the first 4 terms in this sequence will be 2, 3, 4, 5, and it continues in that manner. Then if we have an, this is equal to 1 over n squared. So we're looking for the first 4 terms. So we start with a1. This is 1 over 1 squared, which is just 1. a2, this is 1 over 2 squared, which is equal to 1 over 4. a3, this is 1 over 3 squared, which is 1 over 9. a4, this is 1 over 4 squared, which is equal to 1 over 16. So this is basic substitution. Wherever you have n, you put whatever subscript you are working out over there. So then you list your terms. You have 1, 1 over 4, 1 over 9, and 1 over 16. And the dots to show that it continues, it doesn't just stop there. Some more examples. With an, this is n squared over n plus 1. So again, we want the first 4 terms. So a1, this means in my numerator I have 1 squared divided by 1 plus 1. This is equal to 1 over 2. a2, I have 2, which is my n. I square it, and then I divide this by 2 plus 1. So this is 4 over 3. Then a3, this is 3, we square it, divided by 3 plus 1. This is 9 over 4. And then a4, this is 4 squared divided by 4 plus 1. This is 16 over 5. Okay, so we can list them. The first one is a half. Then I have 4 over 3. I have 9 over 4. And then 16 over 5. And the dots just show that it continues. Those are the first 4 terms. Let's see what happens when we have an. This is minus 1 to the power of 2n minus 1. So it doesn't matter how complicated the formula looks or how it seems, your procedure is always the same. If you're looking for the first n terms, you just substitute n is 1, n is 2, and so on. And notice our index is always a positive whole number because it's term number 1. You cannot have a term 1.5 or 3.5 or something like that. It is first term, second term, and so on. These are discrete values. So a1, this is negative 1, and then 2 times 1 minus 1. This is just negative 1 to the power of 2 minus 1, which is 1. Negative 1 to the power of 1 is just negative 1. Then a2, this is negative 1 to the power of 2 times 2 minus 1. This is negative 1 to the power of 4 minus 1, which is 3. And we say that if you have a negative number raised to an odd exponent, then your answer will always be negative. So this is negative 1. And then a3, this is negative 1 to the power of 2 times 3 minus 1. This is 6 minus 1, which is 5. So I have negative 1 to the power of 5. This is negative 1. And then the last one, this is negative 1, 2 times 4 minus 1. This is negative 1 to the power of 7, which is also equal to negative 1. And if you were to list them, you would see that you have negative 1, negative 1, negative 1, negative 1, and so on. So this is also a sequence. It is a constant sequence. That means every term is equal to negative 1. It doesn't change. So your sequence does not have to consist of different numbers. You can have sequences that consist of only one number repeated over and over. Okay, Then let's look at one more. We have an. This is equal to 2 to the power of n over n squared. So again, this is just substituting. You start with n is equal to 1, n is equal to 2, n is 3, n is 4. Then you list your terms. So a1, this is 2 to the power of 1 over 1 squared. This is just equal to 2. a2, this is 2 to the power of 2 divided by 2 squared. This is equal to 1. And a3, this is 3 to the power of 2 divided by, 2 to the power of 3. 2 to the power of 3 divided by 3 to the power of 2. This is 8 over 9. Then a4, this is 2 to the power of 4 divided by 4 to the power of 2. 2 to the power of 4 is 16 divided by 4 squared. This is 1. Okay, so this is your pattern now. The first one was 2, so we have 2, 1, 8 over 9, 1, and then it will continue. Okay, so that is how we would work out the first n terms in a sequence. If you have the formula, then all you need to do is substitute. Now we have different types of sequences. The first one is what is called the alternating sequence. Now the alternating sequence, we say it is alternating because the signs of the terms are alternating. So you have positive, negative, and so on. So here it's the signs of the terms that alternate. Positive and negative. So a sequence like -1 to -3, 4, -5, 6, and so on. This is what we call an alternating sequence. So what is alternating is the signs of the term. So they go positive, negative, and so on. So one such an times n over here. So this is to the power of n. Okay, so this is the sequence. When we list the terms, this is the general formula for the nth term of the sequence. And then we have what we call the recursively defined sequence. So recursively okay, so this recursively defined sequence, this is what we were doing at the beginning when I asked you if you know the first term, how do you get the next one? So you say you multiply it by -3, and then to get the next one, you multiply it by -3. So a recursively defined sequence is where you have, in order to get the next one, you must know the previous one. So it's recursive. If you don't know the previous one, then you cannot work out what comes next. So each successive term is defined using the preceding term. So here, you can look at an example. So we let a1 equal to 1, and then we let a2 also equal to 1. Then we say an plus 1, this is equal to an minus 1 plus an. Now what this means is if I want to work out the third term, a3, this is just a2 plus a1. So if I look at my sequence or my terms over here, I have a1 is 1 and a2 is 2. So I will say that a3, this is equal to 1 plus 1, and this is equal to 2. Now if I want a4, this is a3 plus a2. So this is equal to 2, so it's this 2 over here, plus the one that came before it, which is equal to 1. So this is equal to 3. Okay, and then I can continue. If I want the fifth term, this is a4 plus a3. Now a4, we just worked it out there, and a3 is over there, so I add the two together. So this is 3 plus 2, and this gives me 5. And then you continue. So you're using the preceding terms in order to work out what comes next. Now this sequence here that I've written, it was 1, then I had 2, 3, 5, next would come 8, and we'll continue in this manner. So here I added these two in order to get that one, then I added these two in order to get this one, I add these two in order to get that one, I add these two in order to get this one, and then the next one I will add I'll add 5 and 8. This is what we call the Fibonacci sequence. Okay, so you might have heard of the Fibonacci sequence before. This is what it is. So it has some very interesting properties that we use in mathematics. You can go and see why this Fibonacci sequence is so interesting, or why we actually study it. Okay, so we can look at another example. We have a1, which is 5, and then we are told that an plus 1, this is 2an minus 3 for n greater than or equal to 1. So here, if I want to work out a2, so here n plus 1 becomes my 2, so n will be 1. This is 2 times a1 minus 3, so this is 2 times 5 minus 3, and this is equal to 10 minus 3, which is equal to 7. Okay, and then if I want to work out a3, this is 2 times the preceding one, which is a2 minus 3, so this is 2 times 7 minus 3. 2 times 7 is 14. 14 minus 3 is 11. Okay, and then you would continue. Let's see, one more, a4. This is 2 times the one that comes before it. Then subtract 3. This is 2 times, the answer we got is 11 minus 3. 2 times 11 is 22. 22 minus 3, this is 19. So this is a recursively defined sequence. So it'll be difficult to calculate the 100th term, for example, because you need to know the 99th. Unless you list them, establish a pattern that is not recursively defined, and then you can figure out what the 100th term is. So with recursively defined, all that means is you need to know the preceding values in order to work out the next one. Okay, so we will stop here for today. Do we have any questions? Anything that is not clear on the tests, the tutorial tests? Okay, If there are no questions, then I will see you guys on Thursday.
Miss,
Yes.